And so on the playlist, you'll have last year's video on this and this year's. You'll see, if you've already watched last year's, it's very similar to what you're going to see today. But like I said, interrupt me if there's a spot in here that you just don't understand. I caught, I think, 2 errors in that presentation too. There's 2 plus signs that should be minus signs. So I'll show you where those corrections were made. But this is an introduction to molecular orbital theory. The last lecture that we had together was really showing you the different scope of local bond theory and molecular orbital theory, and how local bond theory is great for getting molecular structures. It does confirm like the vibrational spectroscopy and rotational spectroscopy because it gives you good molecular structures. When we get to electronic spectroscopy, the structure of the electron cloud, that's where local bond theory fails. And so what is the alternate theory? Molecular orbital theory, and this is an introduction to that. So this is a summary of what I just said. So local bond theory, just to refresh your memory, is that 2 electrons are between 2 atoms and that forms a bond. And so those 2 electrons are local to that bond. In order to get the different shapes of the molecules, we add in there valence shell electron pair repulsion theory, or we sort of swap the E and the S and call it Vesper theory. And that's where hybridization comes in. So if we need a tetrahedral molecule and those angles are 109.5, and we look at the atom, the atomic orbitals, and we see a spherical orbital in the 2s, and we see 3 2p's at 90 degrees, that doesn't line up. And so we form these sp hybrids. We take all 3p orbitals, mix it in with an s orbital, do some mathematical magic, and we can get these hybrids that point out in the corners of a tetrahedron, and we get those 109.5 degree angles. And that's where we get the sp all the way up through the sp3d2. What's going on with the sp3d2 is we need 6 orbitals, and so we start with the lowest ones, the s and the p's, and then we add in 2 d orbitals. That's all related to local bond theory. And when we went to the electronic spectroscopy and looked at the electron cloud, really the bonding depth, the energy of those orbitals, they didn't line up with the hybrids. So those hybrid orbitals were not confirmed by experiment. So then we went into molecular orbital theory, where we can mix those atomic orbitals to make molecular orbitals that stretch over the whole molecule. We will end up getting the same shapes for the molecules, and we'll get a better take on the electron cloud and the energetics and the electronic spectrum. So this today we're going to focus solely on diatomic molecules, specifically homonuclear diatomics. So the same atom on both ends of the molecule. And all homonuclear diatomics are like the X2 structure, you know, whatever atom times 2. And those are d infinity H. And this is the d infinity H character table. And some of the earliest molecules studied were d infinity H molecules. And so they started using the Millikan notation. They gave it Greek letters. That became really complicated when they got to other molecules. And so they switched to A, B, E, and T. Those are the main letters used for the Millikan notation. So you'll see notations on figures for diatomics with sigma G plus and sigma G minus and so on. And you just need to come back to this set of notes and find the key. So sigma G plus is A1G, sigma G minus is A2G, and sigma U plus is A1U, and sigma U minus is A2U. And so this is your key right here, sort of in order of your traditional character table, with A's and G's at the top, and then the E's, and A's and U's in the middle, and then E's in the bottom. Any questions on this? I will, like on the test and so on, use the A's and the E's, not the sigmas and the pi's. Okay. So let's look at molecular orbitals. We're taking atomic orbitals, and we're bringing these 2 atomic orbitals together, and they can be in phase or out of phase, as you can see with the blinking. We have, in the bottom, they're both in phase, so they're blinking in the same time. So and that blinking here indicates expansion and contraction. So they're expanding together and contracting together. So they really mix with each other when they expand together. And up at the top, they're expanding and contracting at different times. And so there's a node in between them. They never really overlap with each other. When one's expanding, the other's contracting. And so if there's no overlap, there's no bonding. And so that's a principle that you can write down. If there's no overlap of the orbitals, there's no bonding. there's no overlap of the orbitals, there's no bonding. And if one part of that orbital is expanding while the other part that's closest to it is shrinking, there's no overlap. Likewise, the core electrons, like in oxygen, the 1s electrons, they're so close to the nucleus, there's no overlap. So if there's no overlap, there's no bonding. So it's only those valence orbitals that are overlapping. So only those valence orbitals are bonding. So for the second row diatomics, those are the 2s and 2p orbitals that are overlapping. But the third row, for like chlorine, those are the 3s and 3p orbitals that are overlapping. So are the 2p orbitals bonding in chlorine? No, because they're held tight, close to the nucleus. They're in the core. So only that valence shell. So if you're in chlorine, it's the 3s and 3p. What about iodine? Come all the way down to iodine, it's the 5s and 5p. And the 4s, the 4p, the 3s, the 3p, the 2s, the 2p, all of those are stuck to the atom. They've been pulled closer because we've added so many protons to the nucleus. Those orbitals are held tightly. And they're not able to overlap with the orbitals on the other iodine. I see that as a problem. I'll talk about diatomics from the second row in class, and then I'll give you chlorine on the test. And I see people doing the bonding with the 2s and the 2p's and the 3s and the 3p. So they have this really complicated MO diagram when it's just the valence orbital. So if you look at a second row diatomic MO diagram, it looks just like the third row, only all the 2's are changed to 3's. And the 2s, the 2p, and the 1s are all held on the atoms. They're not interacting because they're too close to the nucleus. There's no overlap. So here we have overlap. Now that we have a molecular orbital that goes over the whole molecule, we have a much larger box. And so it's in lower energy than the atoms. They have the atomic energies coming in, they interact, and then if you've got a bigger box, it's a drop in energy. And then up here we have a bigger box, but there's more curvature because there's a node. And so that's a higher kinetic energy. So yes, we have a bigger box, but we have a higher kinetic energy because there's a node. We come in with 2 electrons on each of the hydrogen atoms, and they drop down into the lowest energy orbital, and so we have H2 molecule. And those electrons go over the whole molecule, and they satisfy the Coulombic attraction for the nuclei, and so this forms a natural spin-paired bonded molecule. So that's why hydrogen doesn't exist as independent atoms at normal temperatures, ambient temperatures. Whenever they find another hydrogen atom, they form H2 and form this bonding arrangement. This little designation using the 1s orbitals on atom A and the 1s orbital on atom B. If we put a plus sign, we mean they're in phase. If we put a minus sign up at the top, we mean they're out of phase. And so that's the shorthand for those wave functions. Don't worry about the 1 over square root of 2. That's just a normalization constant. And we can talk later about how we come up with that strange 1 over square root of 2. But just mainly I want to put those on there so you can see it's 1s on atom A plus 1s on atom B. And the plus sign shows they're in phase. That's the bonding arrangement. When they're out of phase, there's a minus sign, there's a sign change. That means there's a node between the two. Questions on this before we go on? This is the simplest one. Okay, let's see if questions pop up next. Okay, so also this is the energy difference between the bonding arrangement and the anti-bonding arrangement. And so we can plot that. That's a function of distance. If we pull these atoms apart, again, we'll have less overlap, so we'll have less bonding. We'll also have less anti-bonding. And so we could plot that on a potential energy surface. As we pull the atoms apart, we see that that depth of that well gets shallower and shallower, and so does the anti-bonding repulsion. And so these two middle levels would just come back and join at the energy of the two atoms. We bring them together, they start to interact, you get a bonding and an anti-bonding interaction. And so with vibration, there's a slight oscillation to those two energy levels. And so that causes us to have broad lines in the electronic spectrum. So this also sort of explains why the electronic spectra have really wide spectral lines. because when light comes through, it's like a snapshot of all of the molecules. Some are really close together, some are really far apart. Most of them are in the bonding region, you know, the equilibrium distance. But still, the ones that are far apart absorb a little bit of light too. And so you have a smear of these levels below and above. And so you get all of these molecules absorbing light to go to that upper level. And so then you get broad lines in the electronic spectroscopy. We can label these with their symmetry from that character table. So the bottom one is A1G, the top one is A1U. Is that, no, yeah, A1U. And we have the Cartesian coordinates over here on the right. The z-axis is the axis of symmetry, so that's the axis of the molecule. And so that's pointing up the way I've drawn them. A lot of times we draw diatomics sideways, and so then the z-axis is pointing sideways. So if we move the molecule, we have to move the Cartesian system as well. Okay, so we talked about overlap being favorable. If there's overlap, there's the possibility of bonding. If the orbitals are out of phase, then the overlap is 0, making it an antibonding orbital. And I don't like this picture. I know it's in the textbook, but I differ with this. These little, let's see, where's my pen? Look how these are squished together. If they're out of phase, they're not going to really squish together. They're going to be further apart here. It's going to look more like this. Okay, and we'll see some more accurate pictures later, but I don't like this. This is a node right here, and it looks like those are touching. So I don't like that. What would actually happen is the middle two pieces would shrink and the outer two pieces would grow. And so the electrons are spending more time outside of the molecule than between the atoms. And that's what makes it antibonding. It's not really the node. It's that there's so much curvature in the middle that the electron density moves to the outside of the molecule. And so you have two nuclei that can see each other because the negative charges are on the outside. The positive charges are in the middle. And so that's a repulsive arrangement. And so that's what makes an antibonding orbital antibonding, is that node, that curvature in the middle, squeezes some of the electron density outside of the molecule. So it doesn't help with the bonding. Now here's a more accurate picture of the bonding arrangement. Notice how the orbitals, the atomic orbitals, when they come together, these are two pz orbitals, they come together and there's really a large enhancement of the overlap in the middle where the bonding happens. The electrons are between the nuclei, and so that helps stabilize those two positive charges. We have two negative charges in the middle most of the time, and they're expanding in the middle and then squeezing out to the outside. But that's the Gaussian generated picture of the bonding orbital. Notice we call these sigma and sigma bonds. One of the things that is characteristic of a sigma bonding arrangement is that it has rotational symmetry around the bond. Notice I could spin that object and it would never change color. Right? So it's got rotational symmetry around the bond. That's a sigma bonding arrangement. So you should write that down. That's a great way to determine between a sigma or a pi interaction. So sigma interaction, we call it end-on for the p orbitals, but another or more accurate way is it has rotational symmetry around that bond that it's being joined. This is the pi and pi star bonding for p orbitals. This is side-on interaction, so these p orbitals are interacting from side to side. So the nuclei are there between this is the nucleus here for atom 1 and atom 2. As they get closer, these p orbitals are interacting side to side. And this is an interesting thing to point out, that you have G and U orbitals, right, Gerada and Ungerada, and they do not correspond to bonding or antibonding. Okay, so don't get in your mind that G means bonding, because in this case, G means antibonding. Okay, G and U is just whether it has inversion symmetry or not. And this is an antibonding orbital that has inversion symmetry. So if you'll notice that the 2p on atom A and the 2p on atom B are out of phase, but here's the center of the molecule, and if I start on this part of the wave function and I go through the center of mass to the other side, I have the same sign. And so that means it's a U. I'm sorry, that means it's a G. Why did I say that? Okay, so that's even, that's Garada. And then over here we have the bonding arrangement where you have favorable overlap between these orbitals. They're in phase with each other. We give that a positive sign here. And this is the Ungarada, because if I start here on this wave function and I go through the center of mass to the opposite side, I have a change in sign. And so that's odd, that's Ungarada, so that's going to be it's Ungarada, it means odd. So in the case of side-on interaction, that happens to be the bonding orbital, and the even one happens to be the antibonding, but that's not guaranteed to be the case for the sigma arrangement. Let's go back a page and look at the sigma arrangement. You know, here we have the bonding arrangement is Garada, and the antibonding is Ungarada. See, so you can't associate G and U with bonding and antibonding. Just making sure, because that's a real common mistake. People say, oh, it's antibonding because it's Ungarada, and they don't look at the orbitals. You really got to look at the orbitals to know if it's even or odd under inversion. And now here's the Gaussian generated side-on overlap. And you see how those p orbitals have really expanded to cover the whole molecule. They no longer look like individual p orbitals. They've really spread out and made a full overlapped orbital. You know, so these two p orbitals were in phase, and they really, you know, merged together. So there's a huge overlap, and that's a strong bond if there's a strong amount of overlap. Questions on the sigma or the pi bonds? I can go back or forth if you want.
Can I see the sigma bonds that were G and U for different?
Yes, let's go back. So here are the G and U down here on the bottom left. And so I'll go ahead and write it a little bigger. This is sigma, and that's U, and this is sigma and G. And so let's pick a spot on this molecule, like I'm going to pick right there, and I'm going to go through the center of mass to the other side of the molecule, right there, and I see a change in sign. You see that? And so that's U by definition. And then down here, same thing, I'm going to pick a different spot, just for grins, pick right here, go through the center of mass. It's supposed to be a straight line. Okay. And I see the same sign, so that's G. Yes.
So U and G, you figured out by going through the center of mass.
Yes. And so that's inversion, yeah. And so that's the thing in the character table, that's the column in the character table that tells you whether it's G or U. And so you could just look at that column and say, okay, if I go through, I'm just do the inversion operation. And if you pick one spot in the molecule and it's inverted, every spot in the molecule is going to be inverted. So you just have to find, you know, one spot and go through the center mass to the other side. And if it's changed sign, then it's an inversion. All right. We did the same thing with the arrows, like on benzene. If we had an arrow going out, we went through the center molecule, looked at the other CH bond, and the arrow was going in, and that was a change in the direction of the arrow, and so that was a U. And so these are all three of the, you know, p orbital bonds in nitrogen. They have the end-on interaction of the pz orbitals, and those are form the sigma bond. And then you have the side-on in the x direction and the side-on in the y direction give you the two pi bonds. And so this is a triple bond that have those p orbitals interacting with each other. The s orbitals are also interacting, and so it just gets complicated when you add all of that in. But the s orbitals are interacting in a bonding and an antibonding arrangement. And so you get a positive arrangement, like a bond from the s orbitals, and then you get a negative one from the antibonding. And then the three p orbitals come in and bond. And you have three antibonding orbitals in the p orbitals that are unoccupied. So let's put this in a diagram, and that's what we call an MO diagram. Here's the Gaussian generated pictures. It's the same picture on the left and right, but I changed the brightness because from my monitor to the projector, it's a little bit different in terms of how color saturation is. And so it looks a little better on the right from the projector. You can kind of see all three. Let's just focus on the green. So this donut in the middle is the green for the sigma, and then you've got kind of a hot dog bun here for the pi, and then there's a hot dog bun in the back for the other pi. So you have, you know, 2 hot dog buns for the 2 pi bonds, and then you have a donut in the middle. Man, I'm getting hungry. Maybe I need a bigger breakfast. And so this is let's go back to helium, just the 1s's again. So let's move our way across the periodic table. So we bring helium together. Just like the hydrogen, you can have bonding and antibonding arrangements, but now we have 4 electrons. And so you start at the bottom, 2 electrons in the bottom orbital, 2 electrons in the upper orbital, and now you have just as many electrons in the antibonding arrangement as you do in the bonding arrangement, and so you really don't have a net bonding arrangement. So the antibonding cancels out the bonding, and helium likes to be a single atom, doesn't like to form diatomics. And so later we'll calculate the bond order, but this is a good spot to do it. The bond order is the number of antibonding electrons. I'm sorry, number of bonding minus the number of antibonding. Number of bonding minus the number of antibonding divided by 2. And so we have 2 electrons in the bonding minus 2 electrons in the antibonding divided by 2 equals 0. And so this has a bond order of 0. So it has a 0 bond. If single bond, double bond, triple bond, this has a 0 bond. And so they would fall apart. They come together, interact with each other, but there's really no net benefit for the heliums to get together. If we go back to the hydrogen, we would have 2 bonding and 0 antibonding. Divide by 2, we have 1 bond. So the divide by 2 just means you need 2 electrons for a full bond. So let's look now at the full diagram. This is for fluorine. We've kind of jumped all the way across to the end of the second row because these match the pictures that we've drawn so far most closely. Notice the 2s electron, the 2s region, the 2s orbital region looks familiar. It looks just like the hydrogen 1s and the helium interaction, but these are for the 2s orbitals, in phase and out of phase. Then we have the z orbital, the pz orbitals coming together. Let's look at these designations again. We have the plus and the minus combinations, symmetric and antisymmetric. Then we have the end-on interaction for the pz's. And notice we say that they're plus sign when they're interacting. So technically, if you look at them, you're like, yeah, but one of them is swapped. You know, the 2 pz orbitals, one of them is swapped. But we're going to call plus the interacting, the bonding one, and then minus the antibonding one. And so this is where the sign change from the first video was. This was incorrect in last year's video. This should be a minus sign. It was just a copy-paste error. I copied it up here and didn't change the sign. So I fixed that this year. So this is the 2p z orbital on atom A out of phase. That's what the minus sign means. With the 2p z on atom B. And you see they're out of phase with each other, and so you have that node in the middle. So those are all of the sigma bonding interactions. It seems to be, you know, I keep talking about science establishes a convention, and even though we don't like it, we have to kind of stick with it. Like all the different E's in the character tables, we have the E identity operator, and the E is the second order Millikan notation, and E is energy, etc. But we don't want to change those letters because that's the convention. Well, here's a place where there's no convention. We've not decided how to number the sigma orbitals. Okay. Notice here we have 2 sigma and 2 sigma star. And then we have 3 sigma and 3 sigma star. And that's in this figure from this book. In a different book, we'll have 1 sigma, 2 sigma star, 3 sigma, 4 sigma star. They'll just label the sigmas going from the bottom to the top. And so that number in front of the sigma is pretty meaningless because there's no convention. I can't tell anything from that number. So all I'm going to really be testing you on is whether it's a sigma or sigma star. I can't really complain if you put a 1 sigma and then a 2 sigma star and then a 3 sigma and a 4 sigma star, because there's no convention on how to label these. Okay? So I just want you to know, because you're going to be confused when you look at a different figure and you say, wait a minute, why are these numbers different? It's just different sources, different books. Okay? Yes?
Are we gonna be asked to draw the MO diagram?
Yes, I really want you to draw the Lumo diagrams and practice on drawing the orbitals. At least for the diatomics, you should be good at drawing those pictures. These pictures you should be able to draw. Notice I haven't gotten fancy with these pictures. I haven't tried to draw too much overlap. I just drew the atomic orbitals that combine to make these molecular orbitals. You can certainly do this. If you can draw a p orbital, you can do this. Okay. Because all I've done is taken the p orbitals on the atoms, these 2 p orbitals here, and I've drawn them to where the middle part has the same shading, and that's a bonding arrangement. And up here I drew them with the middle part having a different shading, and that's the antibonding. So if you can draw a p orbital, you can draw these molecular orbitals. And you need to be able to do that, because visually, when you're making a claim in terms of this reaction happens because of an overlap of this p orbital for the transition state with this other thing, you're going to draw the orbitals. And so you need to practice and be good with those.
So will we be given the 3 sigma g? Because I think I could be able to draw the orbitals, because I know that it's the sigma is linear and then g is same. So are we given that?
But as far as the 3 part, it's up to you if you want to call that 3 or 4 or 5. Yeah, and I just number them from bottom to top. That way, I just in order of energy, the lowest one is a 1 sigma. And it happens to be a bonding. The second one is 2 sigma star, so the second sigma is a star. The third sigma is bonding. The fourth sigma is a star. Okay, and I might do the 1 pi, and 2 pi because it's also degenerate, and then the 3 pi star and the 4 pi star. But again, there's no convention for that. So I would not get in there and decide whether you've put those numbers incorrectly. But if you mislabel a star, then that's clearly wrong. If it's bonding, there's no star. If it's antibonding, there's a star. And notice the bonding and antibonding just depends upon whether a node breaks the bond. So look at the bonds. We've got the 2 atoms here. It was a difluorine. And so here's a fluorine, is an F atom right there and an F atom right there. And this has no node in the middle. So that's bonding. Look up here. F here, the bond is between the atoms and there's a node. And so that has to be a star. That is to be a pi star. It's pi because of side-on interaction, and it's a star because of the node. Yes?
Whatever you drew, can you make it bigger so I can't see any change?
Okay, yeah, so there's a node. I put the F's on the atoms, so these are the F atoms here. And then I put there's a node here. Can you see that?
Yeah.
Okay, great, yeah. And so because those orbitals change sign, going from left to right, there's a node there where they don't overlap because one side's expanding while the other side's contracting. And so they're doing this. And so there's really no overlap. And if there's no overlap, there's no bonding. And you can think of these plus and minuses like oil and water. And if they're oil and oil, they're going to mix. And if they're water and water, they're going to mix. And so right here, if you get these 2 close together, and it's oil and water, they're going to form that huge bonding interaction. They're going to suck together and make a molecular orbital that's going to go over the whole molecule. Okay.
So the 2 that you've drawn on are like the examples of how it can be U and G, like opposite?
Yeah, there's that as well. You can look in there and see where the plus signs are, and you can see one is G and one is U. Yeah. And so I've drawn on the p orbital. So here they are, the E1U and the I can't see, E1G. And also the plus sign and the minus sign over here. So these, I've done the PX, 2px on atom A plus 2px on atom B would be, this one here, I guess. And then this is the change in sign the 2px atom A out of phase with the 2px on atom B, which would be this one. Okay. And then the reason it's E, that's doubly degenerate, right? So you could do the X's and then you could do the Y's. And they're exactly the same. So that's why we're trying to show here. This is just the same kind of orbital but rotated 90 degrees for the other p orbitals. See that? So there's a sort of interaction in this plane, and then there's an interaction in that plane. Yes?
So the two in the middle are the X and Y p orbitals?
Yes. So like this, so let's draw the coordinate system on here. This is F2. So let's come up here at the top. We'll draw our normal little coordinate system here, and this is the axis of the molecule, so that has to be Z. The axis of the molecule is the symmetry axis, and we put that symmetry axis as Z. And so then going counterclockwise in our little coordinate system, then X is up and Y is out. So this is X here, and this is Y there. So these would be the two px orbitals, and these would be the py orbitals, because they're coming out of the plane. Did you see that, Ryan? It's kind of small, but the px is going up and down, and the py's are coming in and out. Okay. Yeah. Yes.
So this is for fluorine. So if it was iodine, the only thing that would change would be the two P's and two S's.
Yeah, that's a fantastic question. Yeah, for iodine, it would look the same, only we would come down and we would change all of the 2's to 6's. So it'd be 6p on atom A, 6p on atom B.
I mean 5.
5? Did I? Yeah, okay, my eyesight. Yeah, okay, 5. Sorry. Saw the wrinkled eyebrows. I knew I messed up. So yeah, 5. 5 S's and 5 P's interacting. And then you just ignore all of the others because they're down on the atoms. You think about iodine, it's got 53 protons. So it's really pulling those core electrons in. And, you know, I said that the sodium electron in the 3 shell is near Argentina, if the nucleus is that little red ball in front of target. For iodine, who knows where those 5s and 5, I mean, probably the moon, you know, and so those protons have really pulled in all the core electrons, and those valence electrons are so far out there. Yeah. So let's look at oxygen. And this is a recap of the text. We've been talking about this the whole time. The 2px orbitals side-on interacting with the pi bonds. The z orbitals that are end-on form the sigmas for 3 and 4 here, and then the 2s orbitals are in phase or out of phase. Now this is the same as what was in the last video and in the notes, but I added this morning just to reiterate, only the valence orbitals interact. The core orbitals are too close to the nucleus. So I'm really emphasizing that this year because last year I saw on the test students doing the bonding and antibonding interactions of core atomic orbitals. And so we're not going to do that this year. We're going to only work with the valence orbitals. So that last set in the periodic table, for iodine, the 5s and the 5p, etc. Okay. And so then we have the symmetries of these things, A1G, A1U. Why do we care about the symmetries? That tells us our selection rules. Okay, so when we look at these, we can say, okay, now I've got this, where's the highest occupied molecular orbital? E1G. So this is the HOMO here. Highest occupied molecular orbital, that's what that stands for. And then this is the LUMO, the lowest unoccupied molecular orbital. And so then you could have a transition, the HOMO-LUMO transition is E1G to A1U. And then you go to that character table and you find where light is, and you can figure out if that's an allowed transition. And you also, if you know the energy difference, like if this is plotted and you actually have numbers, you could take the difference between those energy levels, and that would be where the peak shows up in the spectrum. And if it's allowed, you'd see a peak there, and if it's not allowed, even if light came in at that energy difference, it wouldn't absorb because it's not allowed. Yes.
Why do we ignore the other p orbital? Because for oxygen, only one of the double degenerate E1Gs is occupied, so wouldn't the other one be the unoccupied one? Like for fluorine, sure, the top one is the only one occupied, but with oxygen you have.
Yeah, so you've got one electron in each one of those degenerate orbitals, because we'll unpair them first and we'll occupy each orbital independently. One of them is going in the y direction or x direction, one of them's going in the y direction. And so the reason those electrons like to be in their own space is because they have independent view of the nucleus. Electrons repel each other. So if we pair them up in the same orbital, they're occupying the same region. And so then that raises the energy because of the repulsion. So it's lower in energy to put them in separate orbitals. So we couldn't tell. I mean, there's another seat right over there in that other orbital. And so you might be able to find, that is an energy difference, but we would typically label both of those degenerate orbitals as the HOMO, okay? But what you're saying is there would be an arrangement where you pair those up and it would be a tiny little energy difference. That wouldn't show up in the visible spectrum. It might be in the, maybe in the infrared, I'm not sure. But with electronic spectroscopy, mostly we're looking for peaks in the visible region. That would be the HOMO-LUMO gap. And we would label those two degenerate orbitals as the HOMO and then the LUMO being whatever the next one is. Sometimes it's also degenerate, but not in this case. That's a good question. So now we have this weirdness for nitrogen. So that's why I went to fluorine first, and I kind of worked backwards to oxygen. And then we get to nitrogen. What's happening when we get to nitrogen? If fluorine and oxygen, we've got quite a few protons, and it's pulling those electrons closer to the nucleus. And so it's pulling the s orbitals deeper into the nucleus. So for fluorine and for oxygen, the s orbitals have been pulled closer, and they don't overlap with the p orbitals much. Remember, overlap if there's no overlap, there's no bonding. You could also say if there's no overlap, then there's no interaction. So if I pull those s orbitals down and the p orbitals are up here in energy, there's very little overlap, so there's very little mixing, there's very little interaction. But if I start taking away protons, then I relax the pull on all those electrons. And so these orbitals get a little close together and they start to mix with each other. And so for nitrogen, this is only second row, but for nitrogen to the left, really it just applies to nitrogen, carbon, and boron, we see this weird effect where the degenerate pi bonds and that sigma bond swap places. If you'll notice in the middle, this is different right here. This is the only difference between oxygen and nitrogen MO diagrams. Notice in the previous one, let me just back up. In the previous one, look where the pi bonds are, look where the sigma bonds are. The pi bonds are in the middle, and the sigma bonds are on top and bottom. But in nitrogen, these pi and sigma flip. The bonding pi and the bonding sigma flip. And when we did some calculations on this, we see that there's some pi or p character down here in the s orbital in the sigma bonds. So notice we've got some node action going on down here. So that can't be pure two s's interacting. Right? So we have sp mixing. We have some s character up in the p orbitals, and we have some p character down into the s orbitals because they're all close enough to interact. We don't have enough protons to really pull a good separation between the s and the p orbitals. So that's what's going on here. It's just mixing in the s orbital and the p orbitals. So we've got these four sigmas interacting here, and so these are the pictures that we get. So this shows that sp mixing. I'll just circle one and say sp mixing. Notice how it's, if it's going to interact in one way, in one set of orbitals, it's going to be the opposite way in another set of orbitals. And so look at this picture here. See how it interacts, sort of a small s and a big P and a small s and a big P. You see how these kind of mirror each other? Same thing happens up here. This one and this one. So you can kind of see these 4 pairs, or these 2 pairs of interactions. And it's just showing you mathematically what's going on with the SP mixing. I'm not very interested in you learning how to account for SP mixing in terms of your drawings. So the drawings that you will do for the molecular orbitals would be those ones that I showed you on the fluorine. So if you want to write that down, say study the fluorine drawings, not the N2 drawings. So for your drawing behaviors, and you're trying to draw these atomic orbitals, really focus on the fluorine ones. Because we would not know the drawings look like this without Gaussian calculations. So now you do need to know that when there's SP mixing, you get that flop of the pi bond and the sigma bond. Okay, and we'll see a diagram where it becomes more clear. So this is the lithium through nitrogen feature, this SP mixing. And you see that in these 4 sigma orbitals. The pi's are not affected by this, but the sigmas are. And so here are the symmetries for those. It doesn't really change the symmetries of them, but it changes the shapes of the electron clouds for each of the molecular orbitals. We still have the same number, the same bonding and antibonding arrangements. Okay. So let's look now at the series for the whole second period of MO diagrams. Now I've taken off the atoms and I've just kept the middle pieces of those MO diagrams. And when the orbitals, like for the previous pictures, the orbitals were drawn with just 2 straight lines. Now we split those lines side to side. And so let's look at fluorine just to make sure we're stable with what we saw earlier. See, this is just the middle piece of the MO diagram. So here's your sigma, sigma star, sigma, and then up here sigma star, and then you have the pi and the pi star here in the middle. And you can trace all these over to the left and see them right here. So you have the sigma G, sigma U star, pi U, sigma G, pi star G, and sigma star U. And so here are the symmetries for those, and I've colored this one in red because the SP mixing causes it to be up here, but then as we add more and more protons, notice how all the orbitals get pulled down in energy as we add protons. So as we go towards fluorine, we're adding protons to the nucleus and we're pulling harder on those electrons, and they're getting further apart. When they get further apart, there's less interaction between the orbitals. And so we lose SP mixing when we go past nitrogen and we get to oxygen. So this energy level starts to march down. It's the most affected by this, and then it ends up down here below. So you follow that trend. Okay. Now, how do we know this? One experiment is whether the molecule is magnetic or not. So if it has unpaired electrons, those electrons are like little magnets. They're just like spinning charge generates a magnetic field. And so the intrinsic spin on the electron can create a magnetic molecule. And if you pour liquid nitrogen through a magnet, it'll go right through. If you pour liquid oxygen through a magnet, it'll stay. It'll get stuck in the magnetic field. This is a great way to separate nitrogen and oxygen, is to use a magnetic field. And that's fantastic, because you can blow nitrogen and oxygen, cool them all down, like make liquid air, and then run this liquid through a magnetic field, and the oxygen gets stuck by the magnet. Okay, and it gets stuck because of these unpaired electrons. So right here, this shows you that oxygen is paramagnetic. And then this also shows that diboron is paramagnetic. Now, if we didn't have SP mixing, diboron would not be paramagnetic. Can you see that? Look at the energy level diagrams. If that sigma drops below the pi, then the electrons are going to pair up in that singly degenerate orbital. But because the pi's are next, then we have unpaired electrons. This would also, if carbon did not have sp mixing. Put that sigma below the pi bonds in carbon. If we move this down here, then we're going to pair up 2 electrons in that, and then we're going to have unpaired electrons in this pi bond. And it would be paramagnetic, but carbon's not paramagnetic. Dicarbon is not paramagnetic. So it still shows that that level is above in carbon. And then I'm not exactly sure the experiment in nitrogen, because it would give the same result in terms of paramagnetism for nitrogen, whether it had sp mixing or not. But oxygen clearly has this arrangement. So let's look now at the bond order. We could walk through this diagram, and this is something that you need to be able to do very easily, is to calculate the bond order. So it's the number of bonding electrons minus the number of antibonding electrons divided by 2. So you could go through here and calculate the bond orders for all of these. Just notice the stars. Those are your antibonding orbitals. So here's the stars indicated here on the diagram. And I've went ahead and put them on the diagram. So those are your antibonding electrons. So you add up the bonding, subtract the antibonding. So that's your net bonding electrons, and divide by 2, because every 2 electrons makes a bond. And so here are your bond orders. So for dilithium, it's a thing. Okay, who knew? Star Trek. Okay, it's a thing. I don't know about crystals. It'd be very cold, but bond order of 1. But then you get to beryllium, diberyllium, bond order of 0. And then boron, carbon, nitrogen, it grows up to a bond order of 3. And then, why doesn't oxygen have 4? You start putting electrons in the antibonding orbitals. And so it goes back down to 2. Fluorine goes back down to 1. And then you get to neon. You put 2 more in that antibonding orbital at the top, and you end up with 0. And so here, up at the top, is the theory for the bond orders. What's neat about this is you could do cations too and get halves of bond orders. And so you take an electron away from nitrogen, and the bond order gets lower, so it weakens the bond. You take an electron away from oxygen, and the bond order goes up, and it gets a stronger bond. That's weird, isn't it? So you're removing an electron from an antibonding orbital. And so it makes sense. If you're pulling an electron out of an antibonding orbital, the molecule should get stronger. We could do the isoelectronic thing with this too. So what species is isoelectronic with N2? If I take 2 electrons away from oxygen, then I get to N2. It's isoelectronic. Because remember, we're dealing with N2 and O2. So if I take an oxygen atom, if I take 1 electron away from oxygen atom, I'm like nitrogen. But if I have O2 and N2, I have to take 2 electrons away from O2 to make it look like N2. And so O2, 2 plus, would be isoelectronic with N2. And it would have a triple bond. Now that's theory up there with the bond order and the molecular orbital diagram. And our data, look at that, bond energy tracks with bond order. That's amazing. So that next panel is bond energy. And then bond length, it kind of tracks. We've got a weird thing with helium just getting sticky, and it's a van der Waals interaction, so it's not a covalent bond, it's just helium is stuck to another helium atom, and the same with neon. But then the force constant, the vibrational force constant, goes with bond order. So a triple bond is stronger force constant than a double bond, etc. And then up here we'll notice that once again we have something that confirms MO theory and not local bond theory, because local bond theory would predict a quadruple bond between 2 carbon atoms. Okay? Because those carbons have to have an octet. And so we never show freshmen C2. Because they would draw 4 bonds between carbon, and that would be the tightest held diatomic there is, and that's not confirmed by any experiment at all. And here in bond order, it shows that C2 should have a bond order of, what does it say, 2, and then it confirms, what we see in molecular orbital theory, and disproves, again, one more data point against local bond theory in terms of coming up with the number of bonds in a molecule. So we're right at the end. We can do questions in a Kahoot next time to see if you've internalized the material.